Thank you everybody for attending this morning. As Mo said, I think Wednesday morning is always difficult to present, but I appreciate everybody's time this morning. I'm going to talk to you today about a project we were fortunate to do. And unlike university professors in practice, we have to try and get real structures to try our techniques and report back and try and solve problems at the same time. So at Harvard, this is their football stadium. First thing, I would like to acknowledge my co-author, Dr. Shafiq Ahmed, who is pioneering in a lot of the work that I'm going to share with you today. So please don't ask me any too technical questions, but I'm going to do my best to walk you through what we did here at the stadium. So when you looked at the problems, our objectives really was to look at what the deterioration mechanisms were. They'd been reported that ASR was pretty much throughout the structures, and in some places it was undetectable, and in others it was very, very prominent. So our first objective was really to try and identify which ones of these structures did we want to monitor, and what were we trying to establish with that monitoring, with the long-term goal of trying to come up with recommendations to solve the problems. So to do that, like all good studies, we have to break down and try and understand what the mix of the concrete was and where the problems were coming from, what sort of chlorides, carbonation depths, all the typical kind of NDT type work you would do on a structure, and then really develop a monitoring program and really use techniques that maybe hadn't been used before. There had been some strain gauges installed, but the way the structure was moving, the strain gauges were not really giving us much, and they were really just monitoring the crack in one direction and not linear along its length. So just to kind of show you some of the issues, this is some of the structures and some of the supports around the stadium. It's a fantastic stadium. It's been around since the early 1900s. It's, I don't think it gets used more than about 2 times a year, so it's a huge structure that doesn't get used much, but it's very important to the university. So when we look at the mix design, there was nothing that jumped out at us other than obviously there was a reactive aggregate. So that reactive aggregate was what we could see as an internal problem. So what we wanted to do was really look at a technique where we could look at the onset of cracks both on the surface and internal. And then really look at how moisture was playing a role in the whole ASR procedure. So going around the stadium, we did sort of a visual sort of condition state rating where red was in very bad condition, red down to blue, and I'm not sure how clear that is around the structure, but you can see there's not a lot of blue, right? So most of these structures are already on set of ASR, some way more advanced than others. You can see on this, the one that we selected, very visual observations on the surface, and clearly suffering from a lot of problems. So how do we go about it? Well, this technique was done in conjunction with the University of Portland and Thomas Schumacher and Banff University out of Germany. So the transmitters, ultrasonic sensors came from Germany, and our instrumentation came out of Portland University. And the objective here was really to look at the signal that was applied between these two sensors. And really our interest is the back end of the signal, or what they refer to as the Coda wave. This technique has been used in seismic studies, in oil field explorations for a long time, so there's a lot of understanding out there in literature about how you look at this signal. But obviously in concrete, this has never been done in this type of application. So this was a one-off research in the sense of like, what were we going to find, and how do we try and distinguish these signals to understand what the internal cracking migration was of ASR. Because we all know when it's on the surface, then it's a little bit late if you're trying to manage how much cracking is evident when you can visually see it. So my objective here was to try and say to the client, well, if we understand how much it's cracking internally, it will take some time for those cracks to migrate to the surface. So is there a relationship between internal cracking versus surface cracking? So we really were looking at that mechanism. So when you look at this signal, the front end of the signal, it's basically a direct signal. So when you ping this signal, it goes straight from the transmitter to the receiver. But then the back end of the signal bounces around and it will come off of, you can see in these locations, you can see if there's defects, the signal is affected and creates secondary ripples. And then it's these ripples that we're looking to analyze when we look at the signal in detail. So how do we go about that? Well, first of all, you take the signal and you have to understand what affects the signal. So the first thing that we saw was stretch. So the signal is stretched and changed in its length as you start to look at it. So, sorry, the shift, it shifts. So this one's the stretch. So then the next one shifts it and one stretches it. And then the amplitude changes. So these were the three parameters that we needed to create an algorithm that could compensate for these three changes. So this was the challenge, right? So immediately it seemed more of a complex problem than we first thought it might be. So here's an example of the signal where our algorithm was created to basically replicate the signal. So first of all, we had to prove our algorithm would work. So we would make a signal and ping it and calculate it. So you can see here the reconstructed signal is in green, the actual signal is the black, and then the reference signal is red. So when you look at that direct relationship, you can see how they align pretty good, right? So we've got very good alignment here, which is a good indication that algorithm works, and we are, pretty much on track to what we're looking for. So then when we look at the secondary part of the signal, we again can kind of see that we did a pretty good job at making this signal look realistic. So what does that mean in the field? So here's our structure. So we installed 3 transducers. So our original plan was to ping from one to the second and then ping second to the third and so on, so we could get 2 sets of signals. Based on, obviously this has never been done in the field, and never even been done in a laboratory, so we were kind of jumping the gun here a little bit and using this concrete as a big laboratory sample. So we figured that we actually spaced the transducers a little bit too far, so we eliminated one and just focused on 2 transducers and put some amplifiers on them to improve our signal at the surface, so we could get a more distinguishable signal. So this is some data, field data, so now you can start seeing how we just took a sample of the data over a 24-hour period to calibrate back these effects. So you can see how this bottom one is temperature and humidity, and you can start to see how this temperature has a direct relationship with stretch. So immediately you can start seeing how that temperature affects the stretch of the signal. And then by using this temperature and humidity data, atmospheric data, we're able to calibrate these signals back so that we know that when we analyze it, we are taking all these parameters into consideration. So this is basically a set of data that was done, and clearly what you're looking at is you can see that most of the data is in the middle. Okay, this is what you want to see. This means there's no physical change occurring, and these changes are just temperature and humidity changes, moisture level changes in the concrete. These are changes that are normal. So obviously we had 1 year to study this, and that was shortened by a little bit more. So in the end, we got to the point where we wanted to see how effective this system was by putting surface damage. So we actually just drilled 2 small holes into the concrete. You can see hole 1 and hole 2, and see how that affected it. So now if you look at the top of the time shift and the stretch, these what looks like outliers, this is the data after that damage was introduced to the concrete. So this gave us a lot of confidence that the data and the ability for this technique to work was very good. And then subsequently our project ran out, they ran out of money, and we haven't taken this research any further. But we do believe that there's a lot of opportunities for developing this technology even further. So the next I'm going to talk to you about, we also looked at surface damage and mapping, and really when you listen to speakers and you read the literature, there's really two types of ways of looking at this. Digital image correlation, which you can look at deformation, strain, or crack opening displacement. This really wasn't one of our main focuses here, or what we call structural similarity, where we can look at water intrusion, damp areas, crack formation, and spalling. So we really focused on the structural similarity analysis because we really wanted to know, from an ASR perspective, how much this water movement in and out of the surface was occurring. We could also look at a crack and a spored area and use this technique to look for change. So was the crack growing? Was the spore getting bigger? And what surface damages were occurring that could be picked up by this technique? So really it just comes down to pattern tracking, right? So it's a binary, this is binary, so this image here, so it's not a very good enlargement, but this is an odd, there's a feature in this image that looks like this. So if I was to say to everybody, can you find it in that photograph, you'd probably take some time to figure it out, right? So by using a computer, we can do it in seconds, because we really want to create this mathematically by turning this image into pixels and then just applying numbers based on the colors of black versus white, right? So here you can see an example of how that from 0 is black, from above 255, a bit we're white, right? So now we get numbers. When we got numbers, mathematically we can do something with it. So quite easily now, by using some 2D cross correlation, we can take a matrix, a 3x3 matrix and 5x5. Now we can do cross correlation and we can get a number that sums up. That, for those of you who don't enjoy maths. So now we take that image, we apply a 3x3 grid to a 5x5 grid, and we look for the anomaly, and you can see immediately it comes out on the map, and that allows us to be able to pinpoint exactly on that image where that problem is. So that's the principle of the technique and why it's very easy to look and detect for changes on the surface. So how did we apply that in the field? So we took a camera, standard camera, nothing fancy, there was nothing mega expensive, it was just a standard off-the-shelf 12 or 15 megapixel camera that we mounted away from the beam. And of course, one of the things when you mount a camera is you've got to be conscious that you want the photograph to be able to be taken pretty consistently in the same. You don't want it to be moving around, but we know structures move, we know there's vibration, we know that the camera is always. So one of the things that you've got to be conscious of is alignment, right? So the first thing you do with all your images is you've got to make sure you can align them so that your pixels align and everything looks the same. So first of all, this is just one. Now with a camera we can home into different parts of the image and do different things, right? So this one you can see in the blue here, we were interested at this crack, right? So there's a crack here, and our objective was to keep looking at it and see if it changes. So we take images, we took images 4 times a day, basically every 6 hours we took a picture, and even through the night we could take images. So one of the things to look at was the luminance adjustment, because obviously a photograph at night, it looks a lot different than a photograph in the middle of the day. So we have to take that into consideration. We have to align the images, and then we have to compare and identify any changes. So here's an example. This is the crack. So this is 74 days of photographs. And then when you use this 0 to 1, a perfect unchanged image is obviously going to be 1, right? So this is white, and where the image is changed, it's going to become 0, right? So mathematically, now you can start to look at the difference or similarity between day 1 and day 74. So the more and more you do this, the more this change is going to occur, and then by using other methods, you can calculate what that change is and right down to width and length of a crack. And here's an example of just, if you take the two images and then apply the similarity, you can quite quickly see this was just some dust on the surface after they drilled one of the holes. So it wasn't removed, so the camera caught both pre-drilled and after, and then when you run the similarity, you can immediately see there's a change, right? So that is kind of what we're looking for. Here's some other examples of these changes. Again, you can start seeing how the surface of the concrete changes, and how these the red area here, these holes came up because one again collected dust, and that dust was detectable in the hole based on the image on the left. You can see the black rings around the holes indicating that this hole is changed. So for ASR, our interest was to check changes of the patterns on the surface. So now you can see all these different images, and you can see how from one time to another, how they start to be affected by surface moisture. So the whole purpose of that was really to look at the frequency of this water, and that allows us to calculate just how much moisture is going in and out of the structures, particularly around the areas of ASR. And you can quickly see when you look at that in detail, you can see the cracking of the ASR. We know ASR is fueled by moisture, so the areas were very easily distinguishable. The leaking area from the stadium was causing problems with the ASR underneath, and these problems were able to be quantified in terms of how much moisture. We could even predict when it rained there, because we were able to see the change in patterns just based on these images. So we could say, yeah, it started raining in the morning and that rained all day, or it stopped raining about this time because the structure dried to a certain point by the afternoon. So again, there's got a lot of applications for this. If you're looking at buildings and you're looking at moisture movement in and out of a structure, and you want to really do a model that tells you how much of a moisture problem you have, this is a very good technique for doing that, and is just done by post-processing images, basically. This was a concrete spore, so this area had already delaminated and was starting to spore, and this image on your left is obviously you take the top corner, and you use one image to as your base image, so that's always going to be white, and then you correlate that to that image, and then you look for these changes. And here you can see in this scale, you're looking for that to change significantly to identify change that you've been able to capture. So just to conclude, so what did we achieve? Well, we achieved a couple of things. First, we were confident that the Coda wave could detect and monitor internal damage to a structure. Nearly all surface damage, particularly if you're looking at corrosion and or ASR, often starts internally before it becomes a surface issue. So we feel like that's a very good technique for looking at structures where internal damage is really where things start to occur. Image analysis-based monitoring. What we can do with cameras, every time we look at our computers, we don't even need to put our password in anymore. It recognizes us, right, and it logs us in. The technique and the technology at post-processing now of images is so good that you can do so much work with a photograph, and that work continues to be capable of us being able to use those images in engineering to do a lot of cool stuff, right? So again, lots of applications, lots of work still needed to be done, but we feel like it's a very good technique to monitor a number of things: crack length and width, growth. You can do moisture movement on the surface. You can do cracks falling and or changes on the surface that are occurring through other things, even down to things hitting the surface and causing damage. So overall, we felt like our results were great, and really we were looking forward to doing more of this and really taking this work back into the laboratory now and figuring out whether our field application of the techniques can be replicated back in the lab and do further work. Thank you.